Okay, so we will start the second part of this afternoon. We have the great pleasure to welcome Professor Gerhard Rempe, who is a professor at the Max Planck Institute for Quantum Optics in Garching. Gerhard is an internationally known expert with the manipulation of atoms and photons, and I would say his work has been an inspiration for many groups generating photons and trapping atoms and cavities. In our case, the atoms don't need to be trapped, but we are doing similar physics. So Gerhard did his doctorate in Munich, and then he worked in California for a postdoc in the US, and then a professor position in the University of Constance in Germany, before becoming a Max Planck director, which is a very prestigious position in Germany, in Garching, next to Munich. And so he has done a very impressive work in quantum optics. He was one of the first to do Bose-Einstein condensation in Europe, outside of the US. He's right now also a professor at LMU University in Munich. And it's really a great pleasure to welcome here today to share with us all the results he has gathered recently, I guess, on entanglement with both atoms and photons. So thank you, Gerhard, and thank you for coming.
Well, I'm not sure if I can share all the results with you. I would like to present a few selected highlights, let's say. Pascale, thank you very much for inviting me, for giving me the chance to be here, visit your labs. It's a wonderful experience. I have been here before, I should say, invited by Jean Dalibar, who is over there. This was only a few years ago, so I'm afraid there's a little bit of overlap between the talks that I gave before. I understand that this is not exactly in the tradition of Collège de France, but Pascale requested me to talk about multi-photon entanglement, and so there must be some overlap. In particular, when I talk, let's say, or try to give a little bit of a pedagogical introduction into the field for those of you who are maybe not so familiar with this. I mean, Pascale did a wonderful job here, but I try to complement this a little bit. Okay, so thank you very much. Entanglement quo vadis. It's a little bit a view into what I think could be the future of entanglement and where this could be useful. We are making first steps, let's say baby steps in this direction. But as she said, maybe this is a way that we try to outline, that we try to find. Maybe it's a way for other people doing wonderful experiments with different systems, with different platforms, and which are maybe more scalable, which have certain advantages compared to our system. But in some sense, we like what we do, and I hope you like it too. Okay, so entanglement. Let me, for those of you who are maybe coming from the outside, let's give a little bit of an introduction. I'm not giving a full historical account, of course, of entanglement. But entanglement is something that Schrödinger summarized basically in one sentence, which is reprinted there. The best possible knowledge of a whole does not include the best possible knowledge of its parts. It's here. And this is what keeps coming back to haunt us. I mean, to some extent, I would say it's almost clear to consider the whole piece and not just part of it. So why does it haunt us? Well, it has some fancy consequences, which I will not talk about, but which I would like just to remind you, maybe. It gives rise to some non-classical effects, which as a person trained by everyday life is unconventional. It provides correlations which are stronger than classical correlations can be. It provides an effect which is called non-locality of quantum mechanics. which was really bothering not only Schrödinger at that time, but also Einstein, Podolsky, and Rosen, who wrote a very famous paper in the same year, actually, 1935, about entanglement. And Einstein was not happy. Einstein then came up with the idea that maybe there are hidden variables in quantum mechanics, which maybe one can measure, maybe one cannot measure. There's a long story about this. But this was basically a discussion that started at that time. To emphasize this a little bit more, let's say, here's a reprint, so to say, from a book, Quantum Mechanics, which was very, very popular in the 1960s and maybe still is very popular, at least here in France, from Albert Messier. I have no idea how to pronounce his name, honestly. And he talks about the interpretation of quantum mechanics, and entanglement at that time was a kind of interpretation. Interpretation and discussion here, statistical interpretation of the Copenhagen school and so on. And then he basically concluded the controversy that has finally reached a point where it can no longer be decided by any further experimental observations. It henceforth belongs to the philosophy of science rather than the domain of physical sciences proper. So entanglement was kind of a mystery, a philosophical mystery. And that was in 1961, so that was almost 30 years after Schrödinger, 30 years after EPR, Einstein, Podolsky, and Rosen. And not shortly after this, in 1964, Bell came up with an idea of how to test quantum mechanics experimentally. And this is an experiment that was designed by John Clauser at that time in the early 1970s, actually. So again, 10 years later or so, where he could demonstrate a violation of these Bell inequalities. Bell inequalities are classical inequalities, and the violation means that quantum mechanics is correct, and that's what he found. And basically the machine, without going into details here, the machine had a source of photons right here in the middle, a source of photons, of pairs of photons actually. One photon was traveling to the left and one photon was traveling to the right, and was detected here and was detected there. The two photons were entangled in its polarization, and the polarization was measured here, and the polarization was measured there under different angles, and the correlation between the photons violated one of these Bell inequalities. I don't want to go into the details here because this is not the topic, so much the topic of my talk. But it shows a little bit the kind of experiment that was done in the 1970s, and Alain Aspect here in Paris or close to Paris did similar experiments, and this was, so to say, the time when quantum physics was heavily debated in some sense. So let me summarize this basically by saying between 1935 and the idea of entanglement came up, until the Nobel Prize was awarded to John Clauser and Alain Aspect and Anton Zeilinger in 2022, it was basically that entanglement was considered to be interpretation of physics. And finally, the Nobel Prize, of course, and the experiments resolved this interpretation. But in the meantime, things are a little bit different. Now entanglement is considered a resource. And now means maybe starting in the 1990s or early 1990s. Why early 1990s? This can be debated, of course. But in the early 1990s, the idea came up to make teleportation experiments, to use entanglement as a resource for teleporting a quantum mechanical information, a qubit, from one place to the other over long distances. And this is, so to say, the scheme that they invented here, or that they proposed in 1993 to teleport a qubit from one place to the other. And in the meantime, entanglement has been proposed for many applications, quantum communication, quantum computation, and many others really benefit from entanglement these days. So it has become a resource in my perspective. The debate is somehow over, at least after the Nobel Prize. Of course, not everyone would agree to this, maybe, but I think the aspect of application is now kind of dominating. Also, we should say that entanglement is not, of course, not fully understood yet, in particular when it comes to multi-qubits, and I will talk about that. So let me briefly summarize, so to say, the status in my lab, what we have done, just very quickly. I've shown you the experiment of John Clauser, where he has this source and then 2 photons coming out, entangled, and they're propagating 2 meters to the left and 2 meters to the right or so. Now we're talking about entanglement between the city of Munich, an atom sitting in the city of Munich, and an atom sitting at the Max Planck Institute for Quantum Optics. And there's a long optical fiber between the 2 places. The fiber is 24 kilometers long. Line of sight is slightly less, maybe 14 kilometers. And we try to entangle 2 atoms at these distances. We do it differently than the old experiments. The idea is that there's an atom sitting here in the city of Munich. There's an atom which is entangled with a photon. There's some scheme of how to do this. An atom entangled with a photon. The photon then propagates away from the atom. It has a wavelength of 780 nanometer in this case, because it's a rubidium atom, and the resonance wavelength is at 780 nanometer. It's converted, the photon is converted into the telecom regime. So the wavelength changes from 780 to 1514 nanometer actually, and this is a telecom wavelength which is not so much attenuated in an optical fiber, and then propagates to MPQ, which is my institution, is back converted to rubidium wavelengths again from 1514 to the near visible. And then there's an atom sitting here in 2 optical resonators. So there's one resonator like this, the red one, and there's one resonator like this one, the blue one. It's a fiber resonator, so the photon comes in this fiber and approaches this cavity. The cavity is supposed to enhance the interaction strength between a single photon and an atom. Imagine that you have a single atom and just a photon coming. Okay, it flies by. I mean, the atom will not see the photon because the photon has a long wavelength. You focus it down, let's say, to a micrometer squared, but the atom has a cross-section of an angstrom squared or so, which is much, much smaller. Okay, it has an optical cross-section of lambda squared over 2 pi, but again, this is too small to be absorbed with high probability. So that's why we take the photon and reflect it back and forth. And so the atom has multiple chances, let's say, to absorb the photon, can go to the excited state and fall back down, emit a photon, but now in the other resonator. And when there's a photon coming out of this resonator, then we know there has been a qubit photon coming. So this is what we call a heralding receiver. Okay? I mean, there are plenty of losses on the way. There's a loss in capturing the photon. There are losses in the conversion to telecom. There are losses on the way in the fiber. There are losses in the back conversion and so on. But when there's a photon coming out here, we know that a qubit has arrived, is stored in the atom. So then we know, we have a signal, a trigger signal, which tells us this atom is entangled with this atom. Okay? So how does it work? This is for the photon. We first measure, so to say, the photon coming here, not yet the atom, but the photon. And then we see typical correlation signals. For example, we measure the photon in the different polarization bases. It's a polarization qubit, vertical and horizontal, diagonal, anti-diagonal, and so on. And we correlate it with measurements on the atomic qubit in the X, Y, or Z basis. I will come back to that in a moment. But then we see typical correlation signals which show us that entanglement actually exists with a so-called fidelity of 87%. In this case, we can violate Bell inequality by measuring a so-called S parameter of 2.3 with some error bar. And this is supposed to be larger than 2 in quantum physics and smaller than 2 in classical physics, and we clearly see a violation of classical physics here. The rate is about 0.7 per minute, 0.7 events per minute. So this is the atom. It's very preliminary. We are still measuring. But we see a similar correlation, similar pattern here, maybe slightly arranged in a different way, between the different bases in which we measure the atom at LMU and the atom at MPQ. The fidelity has dropped a little bit, the S parameter has also dropped a little bit, the rate has gone down by a factor of 10 or so. So every 15 minutes we can have about an entanglement event. And the entanglement then sits there in a memory. It's stored in this atom, it's stored in that atom, and that sits there and we can use it for whatever we want to use it for. So this is a little bit state of the art of two particle entanglements, two qubit material qubits entangled with each other. But now let's look, so to say, into the future. And in my view, the future is multi-qubit entanglement. So not just two, but many, for a couple of applications. First of all, they're all in the context, or must be seen in the context of the second quantum revolution, quantum computing, quantum communication, and so on. And some of the big questions in the field is, for example, is entanglement scalable? Can we really scale it up to many qubits? And how to do it, and what to do with it? And that brings us to a topic which is sometimes called quantum complexity. It becomes a complex system. Don't worry, I'm not going too much into the details of this complexity. But the whole idea of this complexity is that we can solve problems that cannot be solved on a classical computer, for example. So that involves the concept of entanglement. And then another question is entanglement actually useful? And yes, it's useful because we can build a quantum computer around it, but can we also use it, so to say, very directly in, let's say, quantum error correction? And I think this is where entanglement really becomes useful to correct errors. Every quantum computer, every quantum communication link makes errors because a qubit is something analog. It's not digital, it's analog. And then error correction becomes important, and because it's a qubit, it's quantum error correction, and I think this is very important these days. So these are the two topics I will address in the next how much time? Half an hour is left or whatever. These two topics. So we are talking about photons, mainly in the context that I described before. No? There's this long distance link. We're talking about photons. What is the biggest error we can make with photons? What is the biggest error? What could happen? What is the biggest error one can make with photons? With a single photon. I try to make a single photon and try to give it to you. Will you get it? It flies by. Maybe I don't produce it. Maybe it gets lost on the way. Losses. No? Losses is, so to say, the really bad thing about photons. The largest possible error that can occur is the loss of the qubit carrier, because then the qubit is lost. It's gone. It's away. Kind of irreversibly gone. So what I mean is there's an atom emitting a photon. Maybe they are entangled. Maybe the state of the atom is mapped onto the qubit. And it propagates. Let's say this is Alice. It propagates to Bob. But then long distance and a photon is lost. So there are physical losses like scattering, like absorption, all kinds of things that can happen. And that means nothing arrives here. That's why we need the Herald. No? But the Herald, of course, doesn't mean that we can suppress the losses. The Herald just means it indicates the cases where the photon has actually arrived. In other words, where the photon has not been lost. And the whole idea with the entanglement is maybe we can store the qubit, this physical qubit here, not just in one photon, but in a set of photons. Okay, so now we're talking about several qubits here, several photons in some kind of state. They represent a logical qubit, but encoded in several physical qubits. And then maybe one photon is lost, like this one, or maybe several are lost, but the information is still preserved in this entangled state. That's the hope, that's the idea. Okay? You can't see it from this transparency. It's just an advertisement. It's just PowerPoint. No? But I will try to tell you how we achieve this, or how we approach this problem. So the idea is to encode the qubit in more than one photon. And it relies on the fact that we can build up this multi-qubit entanglement, which is nothing else than a graph state. The graph state that Pascale introduced, I don't know, where are they? There's somewhere here. Somewhere on the blackboard, maybe. Okay, good. So what is a graph state? Now it gets a little bit more mathematical for those of you who know a little bit about physics, but I try to be as simple as possible. So what is a graph state? Well, first of all, we need qubits. Let's say qubits in a computational basis 0 and 1. So 0 is up and 1 is down, for example. Okay? Nothing fancy. Then we have single qubit rotations. A qubit is nothing else than a point on the Poincare sphere. And we need to rotate this point on the Poincare sphere, let's say to the plus case, it's 0 plus 1. And of course there's a minus, correspondingly a minus with a 0 minus 1. Okay, so this is superposition, and it was here. Here. Okay, the light is switched off, but this was a plus. It's actually the same notation. 0 plus 1, it's this state. So that's what we need. And we need gates. We need gates between the photons because we establish entanglement. And this has also been explained here. There's a gate, C0, here, and it's a gate. It makes 0, 0 plus 1, 1. This is an entangled state, and it's made by a gate. So what are the gates? The gates in our case are, for example, control Z gates, which is in the computational basis nothing else than a matrix described by a diagonal. Non-vanishing elements are along the diagonal, 1, 1, 1, minus 1. And everything else is 0. So it's a matrix with all entries 0 except the diagonal, 1, 1, 1, minus 1. And then we just make gates between the qubits as we want. So we prepare all the qubits in the state plus, and then we apply gates on edges, which we define. And I'll show you some pictures in a minute. So we define gates, and then we take the product, and this is a graph state. Okay? So in principle, it's very easy. A set of qubits, you take this and this, and this and this, and this, and so on, in any order, and apply these gates on a state where each qubit is initially prepared in state plus. So that's straightforward. Here's an example for 3 qubits. 3 qubits, like this one. This is 1 qubit, this other qubit, third qubit. This is what we call a linear cluster state. It has 3 qubits entangled by 2 gates. The lines here are gates. There's 1 gate here and 1 gate there. And this is a state that we generate in this way, in the computational basis. Okay, it's just this state here. It's a complicated state. You don't have to look at the details. It's too complicated. And it becomes even more complicated when we go to 4, 5, 6, 7 qubits. It gets a mess. That's why we invent this language here, which is much easier. Here's another graph for 3 qubits. And these are the only 2 possibilities. It's this one or that one here. And this has, in this case, 3 qubits entangled with 3 gates. This is 2 gates, and this is with 3 gates. So there's not much of a difference, and you can see the state that we produce is the same as this one, almost the same, except that the plus 1 here turns into a minus 1 here, and the plus 1 there turns into a minus 1 here. Otherwise, the state looks very similar. Again, you don't have to remember, but remember this one here. It's much simpler language. It's a much simpler language. So just a language that I'm introducing here. No? This language stands for this state, and this language stands for this state. This is what we call a linear cluster state. This is what we call a ring state, a ring graph state, because it's a ring. Okay, so just very simple examples. There's another description I have to introduce, and this is a little bit more complicated. It's a description of graph states in terms of stabilizers. Stabilizers are multi-qubit operators coming from quantum error correction, because they play a big role there, and as you will see, they will play a big role in our experiments. So what are these stabilizers? Well, introduce the typical Pauli operators for the experts, x, y, and z. It's a matrix. This matrix defines the phase flip of the qubit. This matrix describes the bit flip of the qubit. Bit flip means just 0 turns into 1 and 1 turns into 0. And the phase flip is, for example, 0 plus 1 turns into a 0 minus 1. And then there's a y, which is doing something more fancy. Okay, it's a product of x and z. So basically what these operators do, they move our qubit, which lives on this sphere, moves the qubit into different places on the sphere. No? Phase flip and bit flip. And then the stabilizers, by definition, is just the product of the z's, these z's here, the product of the z's in the neighborhood of a qubit. And I'll show you an example in the next slide. The neighborhood of the qubit, and the qubit A, and A is 1, 2, 3, 4, 5. Each qubit is measured in x, and the neighboring qubit are measured in z. And then the graph state is an eigenstate of these stabilizers. Pooh, this is mathematics. It's complicated. It can be shown that this definition of a graph state is the same as the definition of a graph state that I introduced previously in terms of gates. But showing the equivalence is a little bit difficult and a little bit lengthy, and I don't want to go into the details here. So here's an example. So let's consider something like this here. 4 qubits. The stabilizers are here, so I measure, for example, the middle one in x, on the x projected along the x basis, and the other one projecting along the z basis, which are just the different directions on this sphere. No? Z is vertical, x pointing this way, y pointing that way. The product of these measurements is, by definition, 1. So if I measure this one and this one and this one, I know automatically this one. This is a property of entanglement in some sense. No? So I don't have to measure this. Okay? It can even be lost. This is the idea of quantum error correction. This gives me, so to say, as a kind of outlook, these graph states are it's really a nice language, because they allow me to describe operations on the states in a very simple language. For example, I have a state here which is a linear cluster state of 5 qubits, 1, 2, 3, 4, 5, entangled with 4 gates, let's say. And I make an x or y or z measurement on one particular qubit. What happens is, for example, this is the easiest case, I measure the middle one in the z basis. This disentangles this qubit from the rest, but leaves the entanglement here intact and the entanglement there intact. So I can go from a linear cluster state into two, in this case, 2 bell pairs. One entangled pair here and one entangled pair there. Something differently happens for if I measure in the y basis the middle one, then this drops out because it's measured, but it entangles this neighbor with that neighbor. So I'm left with a linear cluster state consisting of 4 qubits if I make a y measurement here. Okay, so it entangles. Or the x, if I measure in the x basis, I'm left with a kind of T. It has 3 qubits in a row and a leaf pointing up. No? Well, not plotted here, but you can see. No? There's this, so to say, this array here with 3 qubits and one moving up. So it's a branches out. So this gives a nice toolbox of how to deal with entanglement. It's really a toolbox that one can apply to larger states to perform some calculations in quantum computing and quantum communication and so on by doing the suitable measurements on the states. That's really, so to say, the beauty about these cluster states. For example, if you have a larger cluster state like this one, two-dimensional, so-called two-dimensional cluster state, and you want, out of these two, you just want to synthesize or to distill just an entanglement, let's say, between this and this one. You just find a path where you make Y measurements, and around this you make Z measurements, and then you arrive at this one. And then you have entangled this qubit with that qubit, given this as a resource. And this can be generalized to quantum computation and so on. I don't want to go into the details here, basically, but the whole idea is to find the root between, let's say, this one and that one, where I can make suitable measurements, and it's a kind of adaptive strategy, no? Efficient entanglement routing based on an adaptive strategy by doing then suitable measurements. So it's really a wonderful tool. What's the optimal, and this is an important point, I think, which is a field of active research, what's the optimal resource is for things like this, like a one-way quantum repeater or a one-way quantum computer, that's not so clear, at least not so clear to me. And I had some discussions this morning with some of your students, and I basically would say they agree. So this is... So now we have to do this in the lab. So here's the lab. Here's a picture of the lab. It doesn't look much more complicated than the lab that John Clauser had, let's say. This is the graph states generation here, and this table contains all the lasers. This picture is a few years old. In the meantime, there's way more optics around it. But in principle, it's not so difficult. In principle, it's just like this. Just like nothing more like this. One atom in a cavity. Why do we need a cavity? Well, we have to tell the atom that the photon it emits should fly in a certain direction. And this is what the mirrors here do. And this atom is entangled with photons. 1 photon, 2, 3, 4. The idea is that it emits a stream of photons all entangled with this one particular atom. This is research that we started in 2007. And we already wanted to make these graph states, cluster states, larger entangled states in 2007, but we failed. We failed because we didn't have the technology available for this. So there's tons of technology behind it. Believe me, I'm not going into the details. You can ask me if you want, but there's really 15 years or so, or more than 50 years of development, which turns out to be very crucial. At the moment, what we can have is an efficiency up to 53% for these photonic qubits, which breaks down into emission probability of roughly 2/3, propagation from here to there of 86%, and a detection probability of 95%, something along this line. So here's a protocol that we do in a more abstract way. We have the atom. We have a set of photons, 1, 2, 3, 4, 5, set of photons. We are making gates, as I said, we are making gates between the atom and the photon. The atom is, so to say, the central piece. It makes a gate with the first photon, with the second photon, with the second to last photon, and with the last photon. And then we can make Hadamard rotations, which basically means we rotate the qubit of the atom between the gates, or we rotate, this is shown here with these yellow things, yellow boxes, we rotate the photonic qubit after they've interacted with the atom, with the material qubit. And depending on where we make the gates, we can make different states. For example, if we have only the Hadamards up here, the rotations of the atomic qubit here, we end up with a linear cluster state, which in our case can have as many as 12 photons. Or when we rotate only here, we can make what is called a G8Z state, which in this language, this graph state language, is pictured by a star. This is just a line with up to 14 photons here in our experiments. And of course, we can do all kinds of mixtures. So it gives us a possibility to engineer the entanglement topology of a set of qubits, and set of qubit means something like a dozen qubits. Here's a result for the G8Z states. This is on the vertical axis is plotted the population or the coherence or the fidelity, which is just the average basically, as a function of the photon number. The GHZ state is kind of an easy state to make because it has only 4 non-vanishing elements in the density matrix. 1 here, 1 there, and 2 off-diagonal elements. And we are measuring basically these 4 states. And what we can see is that, let's look at the fidelity. The fidelity for a small photon number starts at 94%. And we lose fidelity when we go to larger photon numbers with about 1% fidelity loss per photon. And we made this 14 photon state with a fidelity of 80% or so. So we can in principle go further and try to estimate where does this line, the red fidelity line, cross the 50% threshold. The 50% is the threshold to the classical regime. And we estimate this is around 42. 42 is the answer to everything, no? As you know. Of course, we don't know what happens there. No? I mean, we haven't done measurements. So why haven't we done measurements? Well, we haven't done measurements because at that time when we did this a few years ago, this was already the records, and I could not convince the student to go further because it takes some time in the end. No? Probability of 50% or so, and then this to the power of 14 takes some time. Anyway, but we can generate a 14 photon GHZ state about once a minute. So to give you an indication of how successful this can work. Now we turn to the linear cluster states. This is a slightly different protocol with the Hadamard differently done. As a reminder here, these are the stabilizers. We measure in this chain, this entangled chain, we measure qubit number k in the x basis and qubit number k minus 1 and k plus 1, the neighboring ones, in the z basis. And this is what comes out. Okay, so all above 90%. So the local correlation in the neighborhood of each qubit, the local correlation is better than 90%. Ideally, we'd like to have 100%, but nothing in reality is ideal. No? So, but everything is above 90%. So this is a local correlation, no? Because this is local. Qubit k with a neighborhood. How does that relate to fidelity? That's not so clear because this is a local environment and the fidelity describes how well we know the whole state, all photons together. But there's an equation which has been derived already some 20 years ago or so, which relates the stabilizers with the fidelity, but only as a lower bound. Okay, so this is the lower bound here. We also derived an upper bound. We believe we have an upper bound. So the entanglement fidelity of the whole state is somewhere in this red shaded area. So for 12 photons, we are above 50%, and maybe we are as high as close to 80%. So this is roughly the state of the art for, I would say, linear cluster states up to, as I said, 12 photons. We stopped here because we felt that maybe we are going into classical regime and it's not interesting anymore to see what comes after that. So now I introduce another concept in order to make more fancy states that we need. Let me introduce another concept, which is fusion, which is called fusion, graph state fusion. What is graph state fusion? It's a technique which allows us to generate entanglement but without making a gate. So consider, for example, 2 graph states like this one here, GHZ states, 4 qubits here and 4 qubits there, and they're separate. One is here and one is there. Okay? Generated, let's say, by this atom and generated by that atom, but independently from each other. And then what we can do is these are in a cavity, as now 2 qubits in a cavity, not just 1, but 2. And this generates an entanglement, making a joint measurement on the 2 generates an entanglement between the two. And that fuses, that's where the name comes from, fuses this graph state and this graph state together. Now they form a more complex graph state here, a more complex graph state where this qubit here is one logical qubit but two physical qubits, because they're two atoms, no? Two physical atoms, but they form, after the measurement, they form one logical qubit. So basically here summarized, we do a Bell measurement on two photons emitted from two atoms into the same cavity modes. This is how we experimentally do this. I don't want to go too much into the details unless you request me to do this or you ask the question later on. And we made a large number of states with this, and this is maybe the most interesting state that we can offer at the moment. It's a so-called ring state. So again, there are these two atoms, they're both in a cavity. We have local addressing beams which generate the photons, which entangles this atom number 1 with a stream of photons. We have another laser beam which entangles the atom number 2 with a stream of photons coming out here. We repeat this here n times, no? So we have n photons generated basically. And we also have a global beam, the global beam addressing both atoms together, like here, emitting two photons, but we don't, and one left, one right. So this is a post-selection in our experiments, these are detailed. But we don't know from which atom the photon comes, and that entangles the two atoms, and this is basically shown here. And what we then do is basically, well, we start with the two atoms. We start by making a fusion gate. So the two atoms entangle. One logical qubit turns into, two physical qubits turns into one logical qubit. And then basically we are shooting out photons in n times. And that generates a state which is shown here after one photon emission one photon emission step and another one, we are generating this kind of state, and in the end we are doing a second fusion, and then we fuse them together, and then we get a ring state. A ring state means the entanglement topology is that of a ring. Don't think of that as a ring in physical space. We are not sending photons in a circle, no? They are entangled in Hilbert space, if you like, in a ring case scenario. Okay, so this is a complex protocol, and this is the result. For example, we make states like this one. This is 4 logical qubits on a ring. This is 6 logical qubits on a ring, where 2 of these logical qubits are actually 2 physical qubits, atom and photon. And these are the stabilizers, or here, these are the stabilizers, very much like what we discussed before for the linear cluster state. So the stabilizers are, I don't know, all above 80% or so, or around 80%, let's say, and here maybe 75% or so. So it doesn't work perfectly well, but it works reasonably well. That's basically the message. Now we have a technology available to do something with the entanglement. And now I'm returning to the initial question that I was addressing. Can we overcome the loss of a photonic qubit? Encode information in a set of qubits, in a multi-photon set of qubits. So I'm coming back to this state that I described before. Now this is a ring, the ring that we generated in the way that I described. This is a ring here. This is, let's say, the atom. It's one atom. Well, one atom means it's actually 2 atoms, 2 physical qubits, but 1 logical qubit. This is 1 logical qubit. And then we have this ring of photons here. Let's count them 1, 2, 3, 4, 5. And let's assume 3 photons, they are propagating from Alice to Bob, let's say. And now let's assume that 3 photons are lost. Not just 1, but 3 photons are lost. Can Bob retrieve from the information that he gets from these 2 photons, because these 2 photons are the only ones that survive, can Bob retrieve a correlation with the emitting qubit in Alice's position, the atom. Huh? Can she sort of say, or can he, establish a correlation? By the way, this protocol was not discussed in detail, but the idea of using these ring states for quantum error correction was proposed already in 2006, so some 20 years ago, by Manava and co-workers, and they called it a counterfactual error correction. Okay, one can discuss the wording, but anyway, so the question is how to do this, and in this case here, this particular case, it's easy. For example, if you want to measure or want to get information on Z of qubit 6 in the Z basis, after loss of photons 1, 3, and 5, you can just make use of the stabilizer language. So this is a stabilizer around qubit number 4, this one. And by definition, this is X measurement in X basis of qubit 4 and Z basis on the neighbors, this one and this one. Okay, and by definition, this is 1, in the ideal world, of course. By definition, this is 1. So Bob just needs to measure qubit number 4 in the X basis and qubit number 7 in the qubit number 2 in the Z basis. And because this is 1, they know what Z6 is. Even if more than 50% of the photons are lost, in this particular case. There are more cases, like this one. It's a little bit more complicated. This could also happen. Again, 3 photons are lost. I mean, I'm just giving you a few examples. I'm not giving you the general idea. I'm just giving a few examples. So maybe this photon is lost, and that photon is lost, and this photon is lost. And we are interested in establishing a correlation in the X basis, just as another example. So basically, we start with S6. It's a stabilizer around qubit number 6, which would be, by definition, this one here. Z, this qubit measured in the Z basis, and then, sorry, in the X basis, and these 2 in the Z basis. This is the definition. By definition, it's 1. But 4 and 5 are lost. But we can, let's say, with some algebra, change it to this one here. We can introduce, so the X6 is here, the Z4 is there. We can introduce here, exactly at this position here, we can introduce a 1. But a 1 now is a stabilizer around qubit 2. And then another 1, a stabilizer around qubit 3. So we get a somewhat lengthy expression, but most of the expression is 1. So Z, the outcome of a measurement, can only be +1 or -1. In any direction, +1 or -1. The product of Z times Z must then +1. So this is 1, this is 1, and this is 1, and we are left with this one. So basically, in order to establish, for Bob to establish a correlation with the emitting qubit of Alice, let's say in the X direction, he would need to measure qubit number 2 and qubit number 3 in the X basis. And these are the qubits that he has. The other ones are lost. Okay, so these are just few examples, and you can continue, and there are many examples. And to summarize, the whole story is here. We can define a logical efficiency for X or Z measurements versus the physical efficiency. And then there are cases where no photon is lost. There are 5 cases where 1 photon is lost. There are 8 cases where 2 photons are lost, and there are 2 cases where 3 photons are lost. And if 4 photons are lost, then it doesn't work. So the logical efficiency of the whole protocol is just the sum of all this. This is for X or Z. If we think about X and Z, making X and the Z measurement, then this is a little bit more stringent, a little bit more, the boundary conditions are harder. It only works if 1 photon is lost or 2 photons are lost in 5 cases or 6 cases, and we have an equation like this one. Logical efficiency, we call this the entanglement efficiency, because this works in both bases, and this works only in X or only in Z, or maybe both, but this is the end, no? Only both of them together. So now I just plot this equation here. In the next slide, I plot this equation, and this is what we find. So this is on the horizontal axis physical loss, and here's a logical loss. And for just one qubit, if we would just send one qubit, just a diagonal, the physical loss equals the logical loss. It's trivial. But for the ring graph states that I just showed you, it gives, this equation gives these S-shaped curves. It's this one here. It's above, the logical loss is higher than the physical loss when the physical loss is above 50%, but it's lower here when the physical loss is lower than 50%. So there's a threshold here. For this particular case, there's a threshold at 50%. So the prediction is we can have in the communication, we can have a logical loss which is smaller than the physical loss, or the logical efficiency is higher than the physical efficiency if the single photon efficiency is larger than 50% for this particular protocol. That this is higher than 50% is in accordance with the no cloning theorem for qubits, but I don't want to go into the details here. So we made an experiment, and this is the result. Same plot, logical loss, physical loss, but now with data points. There's a data point here, there's a data point there, there's a data point there. Physical loss was high, 70%, 80%, 90% or so. Can you imagine what our reaction was? There's a positive side and there's a negative side. The negative side to this is we have not been able to enter here. We are up here. Please remember, this is the total overall efficiency. Photon generation, photon propagation, photon manipulation, photon detection. It's up here. So these are not bad numbers. But we have not been able to enter this regime here. First message, bad news. The good news is it follows exactly this line. That's perfect. So we have hope. We have hope. And this is so to say, was a very motivating or stimulating thing. We had hope that we should continue here because the theory, we were convinced that the theory behind the experiment is correct. So we were along the correct line. Okay, so we had to reduce the physical loss. Pooh, that was hard. It took, I don't know, a year or so to optimize all the optical elements in the system. Narrowband coated lenses, broadband achromatic doublets, mirrors, filters, wave plates, blah, 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 many things. There are several of these mirrors and filters, etc., etc. This is the efficiency in the end that we achieved. They're all 99.8, 99%, 99.9 now, no? After optimization, which means there's a total efficiency of something like this here for each of the elements. Okay, and after optimizing this for a year or so, we were finally able to get two more data points. One more data point is this one here, and one more data point is right in the regime where we want to be. So this here shows an inset. So we have, I don't know, 48% or so of loss. So that means 52% efficiency. Generation, propagation, manipulation, detection, everything included. And we are certainly in this regime where we want to be. And it even looks a little bit like we are better than theory, which I still don't believe. But this is what comes out. This is what comes out. I think this is the first time that loss tolerance is observed for photons. There's no post-selection here in the experiment. Absolutely no post-selection, just straightforward. That's okay. Having said that, there's one post-selection. This one post-selection is we are post-selecting on the presence of two atoms. Of course, we need two atoms, no? to make the state, to make the ring state. If there are no two atoms, we can't make a ring state. No? So we are always looking into the system and post-selecting on that before the experiment and after the experiment, there are two atoms emitting the photons. So that's the only thing we do. but there's no post-selection on the photons or whatever. And this is why I think this is really the first time we can see this. Now comes, so to say, how to proceed. How to proceed from here. Of course, we would like to have physical loss which is even smaller. And one of the motivations is this entanglement efficiency that I mentioned before, where we have X and Z measurements, and not only X or Z, or both. But now the idea is, so to say, to look for the entanglement efficiency in order to really have two qubits entangled at a distance in the presence of losses. And then what happens is this other equation that I showed you, expressed in blue, and this is the prediction. And now we have a prediction here at around 30% or 32%, 68%. So there's another threshold. There's another threshold which we have to overcome. Okay, so we were here, and now we have to go there. And I have to disappoint you, this hasn't worked so far. I can basically only tell you that the idea that we have in mind of maybe how to even increase the efficiency further beyond this 52 or so percent. It's a big step towards 30%. No? It's a big step. So one of the ideas is basically to do a kind of multiplexing experiment, very similar to what I've shown you before. Please remember, the ring had 6 logical qubits, but 2 of them were 2 physical qubits. Now maybe the idea is to have a cavity with not only 1 or 2 atoms, but with 4, 5, 6 atoms, whatever, and consider them all together as one logical qubit, which emits photons. It's a vague idea, let's say. Because then, and this is what we have shown experimentally in this paper here, and then the efficiency as a number of atoms into the fiber, let's say, at the output of the cavity goes from, in this particular case, 30% or so, almost to 100% here. So the idea is not to increase the cooperativity. This would be one possibility, to have better cavities, let's say, with less losses and higher cooperativity in order to steer the photon better into the cavity mode. But to have just a couple of atoms here. And in this way increase the efficiency. And we have done the first step with the multiplexing here. We have done the first step into this direction where we approach very close to 100%. So that's one avenue we are thinking about, maybe to do next. And of course, the ultimate goal is something like, I don't know, a quantum internet. With many nodes on long distance with repeaters in between. So all these little dots here are repeater nodes. And then we entangle, so to say, we entangle all of them, and then by making suitable measurements, for example, on the repeaters, Z measurements, and the repeaters are dropping out of the system. And in the end, we are maybe left with the larger states like this one. This was a proposal, or I took this picture from one of Dagmar Bu's papers already 10 years ago. And you can realize there are all these gates here, very much as I described them before, gates and repeater stations and so on, network nodes. So this is, of course, the idea that if there are many photons coming out, one photon goes to one material qubit, the next photon goes to another one, and then they are sitting in an, let's say, material network, distributed network of material qubits. And at the moment, I cannot show results yet, but at the moment, we have a 3-node network where we distribute, so where we entangle three different nodes, very much along the lines that I've shown you before. So it looks like it's working. So let me summarize. What did we achieve? Well, I outlined, so to say, the quantum, or mentioned the quantum complexity and quantum error correction ideas. So the quantum complexity, the message to you is we can generate arbitrary entanglement topologies at will on the push of a button. And even small-scale entanglement topologies, in our case 6 logical qubits, are useful in beating classical physics. So they're really useful. The efficiency of communication can be higher than in the classical case. So this is under the headline of quantum error correction and quantum complexity. So we don't need, this is sort of say my statement here. Quantum computer is of course a fancy thing, but it needs so many qubits that it's hard. That makes it hard. But in quantum communication, maybe smaller number of qubits, as I've shown you here, smaller number of qubits might already provide some useful thing. This is so to say the message behind this. Okay, and the last slide shows a little bit the topology of the states that we generated. This was the 14 qubits G8Z state or star-like state. This is a 4-qubit ring, a 5-qubit ring. I didn't show you. This was a 6-qubit ring. We've also generated 3 states like this one here. This is a tree. There's a root here. There are branches. There are leaves. So that's how they're called. I didn't tell you about. And we have these linear cluster states and so on. So this is the zoo that we have to play with at the moment. And I should also, of course, mention my co-workers, which are the most important people here. Olivier, actually a French postdoc who was with me for many years already. Wonderful person, wonderful scientist. Together with Leonardo Russo and Philippe Thomas, 2 PhD students. And some of the results that I was presenting here was done in collaboration with Anders Sørensen and Stefano Pesani and a PhD student, Love Pettersen, at the Niels Bohr Institute in Denmark. Okay, I took probably too much time, maybe? No, it's exactly, it's 1 hour, okay. It's 5 minutes too much, no? Okay, anyway, thank you very much for your attention.